Thank you. This is the rerun of the talk I gave in Zoom, unfortunately, 5 months ago in Prague, where I haven't been to. So those who heard it before will have to suffer again. Danny asked me to explain the Latin part. You can look it up in Google. It means through hardship to the stars, whatever that means. Signifies how I feel about the area. It will be kind of a tour of a significant part of computational and combinatorial geometry that I've been involved in over the past 40 plus years, together with many students, some of which are very new, and many colleagues. Okay, so I start. It's also presented in some sort of chronological order, and almost surely I will run out of time, which is typical with me, but never mind. So we start with motivating the area by algorithmic motion planning. In this example, you have a rich polygon, free to translate and rotate in the plane. So it has 3 degrees of freedom, 2 of translations, 1 of rotation. And you are given a start and a goal placement, and you ask, and there are obstacles polygonal in this illustration, and you ask whether you can move the robot from the start to the goal configuration without colliding with anything. This is the standard motion planning problem. Of course, the number of degrees of freedom can be as large as you wish. You can have a swarm of robots moving independently. But anyway, you have some numbers D of degrees of freedom. And the way to model the problem is to represent each placement of the robot by a point in D-dimensional space, whose coordinates gives the parameters that define the placement of the robot. And this is called configuration space, which is split into 2 parts. The free part, where the robot does not collide with an obstacle, and the forbidden part where it does. And we are interested in the free space. We want to compute it to have some discrete representation of it, so that if I give you the start and the goal configuration, you can locate them in this representation and determine whether they can reach one another by a path that only goes through 3 places. Now, the thing to observe is that when you move from free to forbidden, it happens when you make contact with some feature of you is making some contact with a robot feature, and then you lose 1 degree of freedom and you get a surface, a B-1 dimensional surface in the configuration space. So there are 2 questions to ask. One is to compute the entire free space, and one is to compute just the portion of free space consisting of placement that you can reach from your start position, which is presumably a smaller subset of the free space. So you can see how a contact surface look. A vertex of the robot in this case touches an obstacle edge, and on the right you can see how free space can look at. The blue are the contact surfaces. What is shaded is one connected component of free space that contains a starting position marked by the black dot, and you want to compute either that or the entire thing. The first goal, which is the more general one, has been solved in a paper called Piano Movers 2. It's the second paper in a sequence of papers I wrote with Jack Schwartz many years ago, and I'll say more about it later. But let me kind of stop with robotics and move to geometry. So the setup that we face in the motion planning is that we have a collection of surfaces, these contact surfaces, for example, the D-1 dimensional surfaces in D dimensions. Think of lines in the plane as the simplest possible example, and we are interested in something called the arrangement. It's the composition of space into connected pieces that you get when you lay down all your objects on top of one another. They cut the space into pieces, and each piece is formally defined as a maximum connected component that is contained in some fixed subset of the object and is disjoint from everything else. So, for example, this would be an arrangement of lines in the plane. There are two types of cells in this case: a zero-dimensional cell of a vertex lying on two lines disjoint from everything else, an edge, maximum connected piece of a line not disjoint from all the other lines, and a two-dimensional face not contained in anything and disjoint from everything, maximum connected. Now, before I continue, in general, we deal with curves or with curved surfaces in higher dimensions. So we will assume, as is typically done, that they are all algebraic of some fixed degree. But that doesn't solve the problem, because we still need a model where we can manipulate any small number of them. For example, if I give you two curves and ask for their intersection points, I need to solve two polynomial equations in two variables. And in general, that's not easy. It cannot be done by radicals. But at any rate, I want a model where I can do this exactly, whatever that means. And I will not go into what it means, but there is such a model. It's a whole area adjacent to this area called computational real algebraic geometry, which has been beaten to death for many years. The textbook Bible of the area is the book by Basu, Pollack, and Roa, where you can find anything that you want to know or you don't want to know about the topic. So, in short, the algebraic issues can be handled. They are not very cheap, but they will take constant time in the curves of constant complexity, and I will ignore it completely in what follows, just to know that you can do it. Now, the two sub areas or whatever of what I'm going to talk about are combinatorial and algorithm. And they are kind of, one is combinatorial and the other one is more computer science-like, but it turns out that they go hand in hand together quite a bit, and you can exploit it to pass from one to another. Usually, you first have to solve a combinatorial problem, because if I ask you to construct a structure X, the first thing you have to tell me what is its worst case or whatever complexity. Because if it is quadratic, you will not be able to solve it in n log n time, for example. So it's a lower bound and also a motivation for an upper. So we will see in this talk how these things are intertwined. So we are interested in arrangement, and let's start with the simplest example, lines in the plane, n lines in the plane. First, just combinatorial aspect. So you look at the arrangement and can ask various questions. For lines, many questions are trivial. What is the complexity of the entire arrangement? It's n squared because the number of vertices, intersections of pairs of lines is n squared, and Euler's formula will tell you that everything else is also quadratic. What is the complexity of a single cell, single face of the arrangement? It's linear. It's actually at most n, because you can think of it as intersection of n half spaces, each bounded by two lines. Lower and upper envelope, which is a special case of a single cell, are also a linear complexity. But even in this quote-unquote trivial setup, you have very deep questions. Let me mention two of them. One is the k level. There is another parameter k, and we should picture it the next slide on the left. So it's the collection of all the edges of the arrangement that have exactly k lines below them. The way to think about them is that you start at the west end on one of the lines and go to the east, and every time you reach a junction, you must make a turn. And the number of terms that you will make is the complexity of the K level. It's easy to see that this is exactly what you need to do. But here, what is the complexity? How many such terms will you make in the worst case? Nobody knows. There is an upper bound of n times k to the 1/3, and there is a lower bound that is only slightly superlinear. And the gap is by now more than, not more, but about 30 years old and completely.
Micha, what do you think is the truth?
I find it hard to believe that nk to the 1/3 is the correct. I'm sure that it should go down in linear, but having said that, I have no further idea. The other problem is many faces. This is a problem that has been solved. On the right, you see an illustration with circles instead of lines. Doesn't matter much. So each face is represented by some point contains, and you want the overall complexity, the sum of the complexity of all the faces together. And then at least we know the answer, which is roughly m to the 2/3 m to the 2/3 n. And if you look at this bound, the 2/3 will arise, and similar things will arise later in the talk, quite a bit. Okay, now, but the interesting thing is that we don't have arrangement of lines, but arrangement of curves, so arcs, and the simplest example would be an arrangement of segments, line segments. All hell breaks loose there already, and it just gets more complicated as you look at more general things. The complexity of the entire arrangement is still quadratic. That's not very interesting, but what is the complexity of a single cell, of the lower or upper envelope? Not to mention K levels and many cells, which are even harder. Okay, here is a single cell, here is the lower envelope. Lower envelope, if the curves are X monotone, you can think of the lower envelope as the pointwise minimum of those graph of those curves, each representing some function. So the key question. So the key concept here in the header is Dirichlet-Schinzel sequences that I will talk about in the next few slides. So let's think about the case of segments. Again, if you think of each segment as the graph of a partially defined linear function, the lower envelope is just a pointwise minimum of these functions, which will be a polygonal curve, and it may have jumped discontinuity as you go through endpoints of segments. How many pieces will the envelope consist of? And here you can formulate it as a purely combinatorial problem by mapping the envelope into a sequence. And so here is a nice example of 6 segments forming quite a complicated envelope. And as you walk below the envelope from left to right and just write down the names of the segments that appear on the envelope, you will get a sequence. 1, 2, 1, 3, 1, 4, etc. And the question is, how many segments? That would give you the complexity of the. What is the maximum number of such things that you can? Here you get, by the way, 22. So it's quote unquote large. So the answer, again, hopefully some of you already face these things. The answer is proportional to n alpha n. It is with a rather small constant of proportionality, something like 2. So the lower envelope of n segments will have at most n alpha n pieces, where alpha n is the intersectional function. It increases to infinity as n grows, but very, 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 very slowly. And it has been studied during the 80s in a sequence of papers. And the initial insight that led us make progress on the problem is to realize that it is related to Tarjan's analysis of the union-find algorithm, where there you also have an alpha factor, but now it's a physical. I can construct with sticks, nails, and a hammer something that will have n alpha n pieces on the lower end. Okay. In general, this is just a case of segment. In general, you can have arcs, you can have functions of all kinds, and there is a parameter S that comes from a sequence, and a partitioning sequence of order S on n symbols is a sequence that satisfies the following two conditions. The first condition is that you cannot write the same sequence twice in a row. You cannot write 1, 1. If you want to write 1, 1, you have to write something in between. And the other more interesting condition is there is no pair of symbols, A and B, that appear in the sequence in alternating S plus 2 times, not necessarily consecutive. So you cannot have an A, followed later by a B, an A, and a B, and so on, S plus 2 times. Then it's a sequence of order S. So for example, for segments, as it turns out, S will be 3. So you don't want an ababa, A, B, A, B, A. And here is the sequence that we saw before, and I just chose 2 symbols, 2 and 4, to show you that you get 2, you can get 4, you can get 2, you can get 4, but you cannot get another 2 later. So it's a downward sequence of orders, and we denote its maximum length by lambda S of n, and it's not difficult to see that this is equivalent. So every double partitioning sequence is realized as the lower envelope sequence of n functions, every pair of which intersect at most S times. Now you may object because segments do not intersect at 3 points, but only once. But if the functions are partial, you have to add 2 to the index because the endpoints allow you to get 2 extra alternations. Anyway, let me skip this to illustrate why it is really equivalent. It's not difficult, but there is not much time. It's called double partitioning.
So what is the bit complexity of the solution?
Say it again.
What is the bit complexity of the solution?
I'm not sure I heard.
The bit complexity.
The bit complexity.
Actually,
that's a good thing. When you look at the lower bound construction, you use things of lengths that are astronomically different from one another. I don't know if anyone has other boundaries, but I would assume that it is large.
you cannot get an alpha n columns.
I would rather ignore the question because I really don't know. But quite likely it would probably be larger. Okay, Downford and Schimsel wrote introduced the sequence to the world and wrote 2 papers called A Combinatorial Problem Connected with Differential Equations, a very mysterious name. They are connected to differential equations, but they are connected to lots of other things. They were brought into geometry by Micha Sharir in the early 80s, and then we worked on it and managed to get the type 1. Now, I mentioned that lambda 3 of n is about n alpha n. By now, the coefficient 2 is also known. Lambda 1 of n and lambda 2 of n are 2 exceptions where lambda 1 is trivial, for lines, for example, and lambda 2 is a nice exercise if you have nothing to do. It's a nice homework exercise. Every lambda is of the form n times some function of alpha n. Lambda 4 is n times 2 to the alpha n, and so on. It keeps growing, but this growth is ridiculous because alpha is quote unquote a constant, which it isn't, but still. Okay, and this thing was born because of lower envelopes in geometry, but it appears all over. For example, the complexity of a single cell, which is more complicated to analyze because of all the possible topological structures that are true, it is still lambda s of n with some constant, or lambda s plus 2 of n if the curves are bounded. And there are many other, really a huge number of applications. Let me just say quickly what happens in higher dimensions. So for example, I have lower envelope of surfaces or surface patches in 3 dimensions. Then we can show that the envelope complexity is roughly quadratic. All star simply means that I don't write small factors like n to the epsilon or polylog or something like this. So to keep the notation a bit cleaner. So that was proved with dummy, but there are very few cases where we can really prove a bound that involves double Schinsel factors. For triangles, it is known, but in general, it is open. We only have this near quadratic bound, and in higher dimensions, the envelope complexity is n to the d minus 1. Instead of n to the d, which would be the complexity of the full arrangement, so we gain one order of magnitude, so to speak, and the complexity of a single cell, which is much more complicated to analyze, is also n to the d minus 1, shown with a paper with Dani, and then Basu extended in 3 dimensions, then Basu extended it to n dimensions. Ignore the last sentence.
Those are upper bounds?
Mm-hmm.
So on upper bounds?
Also lower bound, but the factor is maybe a bit different. Yeah, you can get lower bounds. Okay, so once we have all those findings, we can go back to motion planning. So we know that the complexity of the component of free space that you can reach from a fixed point, which is a single cell in the arrangement, is n to the d minus 1. The complexity of the entire space will be n to the d. So when d is large, the saving is not so impressive, but when d is 3, like the case the moving polygon, you get roughly n square solutions instead of n cube. That's already significant. And you can, in some of the cases, you can even bring the complexity bound to something that involves the double Schinsel. Okay, so these are a couple of slides that I'm not sure pedagogically is the right thing to say, but let me say anyway that if you really want a complete solution of the motion planning problem, you can do it, as was shown in this Piano Movers 2 paper. And the key concept is something called cylindrical algebraic decomposition. We now actually are slowly sliding into the algorithmic aspect of the talk, because, I mean, it's still combinatorial what I'm talking about, but it is used for an algorithm to do motion planning and everything else. You are given a collection of polynomials in d dimensions, d various, and you want to decompose space into pieces. Each piece should have constant complexity. It would look like a curvy prism, so to speak. And within each cell, all the polynomials have a fixed sign. I mean, each of them has a fixed sign. So yeah, each such cell, and if the polynomials are those that define the contact surfaces, then each cell is either fully free, you don't cross any, excuse me, you don't cross any contact surface within the cell, or it's fully forbidden for the same reason. You compute the free cells, you connect them somehow, and you get a representation of free space, which is what you want. Here is an illustration. The yellow would be the free space. The way it's not easy to define cylindrical algebraic decomposition, but roughly say in the plane, you take each point of interest, x extreme singular intersection of two curves or whatever, and you draw a vertical line through each of them. This partitions the plane into vertical slabs, but within each slab, the functions, the graphs of the function do not intersect. They are stacked upon one upon the other, and you get a sequence, an ordered sequence in the y direction. So you have a sequence along the x-axis intervals, and over each interval you have such a sequence. Formally, every cell in the decomposition would look like x1 lies between two values, x2 lie between two functions of x1, and so on, and xt lie between two functions. So you can have equalities, and then you get lower dimensional cells. It's a very nice structure. First of all, it's very structured. you define it as I showed you, and it's very easy to search. If I give you a point and ask which cell contains it, you first take its x coordinate and looks at the first set of intervals of the x-axis. Then you take its y and locate it between the curves in the second dimension. Keep going until you get the cell that contains the point. So if I give you a placement of the robot, you can, in logarithmic time, tell me whether it's free or not, and you can plan a motion between two placements using the same structure. But the catch is that this is extremely expensive. The number of cells is doubly exponential in the dimension and in some other parameters. So it's not a very good structure, but still it gives you a solution. It hides very heavy-duty algebra to obtain this decomposition involving resultants and sub-resultants. I don't want to say anything more about it. But it gives you a method to do a space decomposition, which is useful to solve problems using divide and conquer, which I'll show you in a minute. So so let me abandon this general thing and go down to simple instances. And I use something called Hopcroft's problem as a motivation. A Hopcroft problem, named after Hopcroft, who asked it, gives you a set P of m points in the plane and a set L of n lines in the plane, and asks, is there a point in P that lies on the line in L? Is there an incidence, another important concept here, between a point of P and a line? Of course, in m times n time, in m times n time, you can really solve it, but you want better. And the main idea is to do something like the cat, to chop up space into pieces, so that each piece will be intersected by only a few lines and contain only a few points, and then solve the problem by a weaker algorithm in each cell separately. The key concept here is something called 1 over R cutting. There is another parameter R, and it is defined on the lines. You cut space into things shown here in green, vertical trapezoids or triangles, so that each of them will be cut by n over R line, at most n over R lines. And a simple packing argument showed you that you need at least R square cells to do it, but you can do it with R square cells. And there are also points. You can also guarantee that each cell contains at most n over R square points. Otherwise, you chop cells into subcells. The number doesn't go up significantly. So Hopcroft problem is always follow. You construct a 1 over R cutting somehow, and in each cell you get a set p tau of the points it contains and a set L tau of lines that cross it. You move to the dual plane, a standard concept in computational geometry. Points become lines, lines become points, and incidences are preserved. And so now you have m over R squared lines and n over R points. So the number of lines is much smaller, so to speak. You compute their arrangement and locate all the points in the arrangement to find whether some point lies on a line. These two operations are standard in computational geometry, but I don't have time to say anything about them. They are called line sweeping and point location. Let me just say that Tarjan and Sarnak and Tarjan found an optimal algorithm to do point location in the plane. Locate a point in an arrangement of lines or whatever, and they liked it so, Tarjan liked it so much that he chose it as a topic of his Turing Award lecture, long time ago. Never mind. It turns out that you can construct the arrangement in time that is roughly quadratic in the number of dual lines, and you can locate each point in time that is logarithmic. So you get something like p tau squared plus L tau. And since p tau is m over r squared and L tau is n over r, the sizes, this is the time that takes you to do it per cell. There are r squared cells of the cutting, you multiply and you get this term, expression, and then you choose r to balance the two terms, which is m to the 2/3 over n to the 1/3, and you get this bound. The m to the 2/3, m to the 2/3, they're already seen. The m plus n you have to add for extreme cases where m is much larger or much, never mind. And this bound is essentially tight, algorithmically. Okay, so this was algorithmic. Now let's look at the combinatorial twin of the problem. So we have sets P and L as before, points and lines, but now we don't want to compute anything, we just want to bound the number of incidences between the points and the lines. So we want to bound the number of pairs point lines, such as the point lies on the line.
I have another question you might want to ignore.
You may ignore this.
Yeah, so
What?
when you say that it's optimal, what do you mean? In what model?
It's a good question. You have to assume that the model only does comparisons of a certain kind and so on. It's not the strongest, but there are normal models where the normal. Again, algorithmically, it is more cumbersome. Combinatorially, you can ask whether it's a low bound and it's self. Yeah, of course, yes. Okay, so how many incidents can you? Again, m times n would be a trivial bound. You want to do better, and essentially you follow the Hopcroft's algorithm, almost verbatim, except for one step, where in the Hopcroft thing we talked about computing, locating points in an arrangement of dual lines, and here we use the same looking bound on the number of incidences between points and lines, written above. Let me just tell you how to do it. It's a very nice trick. You charge each incidence PL to a pair of points P and another point P prime on the same line. Now, and you want to count the number of these pairs. Now, if I give you such a pair, you know the line. There is a song in Hebrew that through every pair of points, there is only one line passing through them, but that's also true in English. So this number is simply the square. But what if the lines does not contain a second point? Too bad, but then it has only one incidence, contains only one point. So we add L to the bound, and that's the weak bound. Now, since the bound looks exactly as the Hopcroft's algorithmic bound, we will get exactly the same solution, the same way, cutting and everything, but there will be no O star, no hidden factor. This would be the bound on the number of incidences between points and lines, and it is tight, as shown by Erdesh, Elekesh, all kinds of other people. The original paper is by Semeredi and Trotter, unreadable with something like 10 to the 13 constant of proportionality, but as you can see, it has been simplified considerably. A reviewer to one of my papers commented, not very critically, but still, that the study of incidences has become a cottage industry. Like people sitting in back rooms and churning out one bound after the other, and probably underpaid to do it, but never mind. So, and indeed, there are many types of incidences that you can study. For example, you don't need lines. You can ask for incidences between points and circles, points and other curves in the plane. You can go to higher dimensions, points and curves, surfaces. There is an end, but not a small end to what you can ask. And what you get is all kinds of mysteriously looking fractional bounds like this 2/3, 2/3. Almost all of them are suspected, are not known and strongly suspected not to be tight. The case of points and lines is the only good case, so to speak, or one of the very few cases of polynomial. What I like in particular is the bound for circuits. It is, by now there is no hidden factors here, and the bound is m to the 2/3, m to the 2/3, like for lines, plus m to the 6/11, n to the 9/11, plus m to the 7.
Those are points and circles.
Points and circles, yes, in the plane. The last improvement, only less than a year old, has knocked off the last polylogarithmic factors that was known before. And again, the 2/3 is tight. The 6/11, 9/11 is very, very likely not tight. Okay, so we've seen how, let's again go back to the algorithmic part. We have seen how cuttings are used to solve algorithmic problems. In general, you can be in d dimensions and you have a collection of surfaces, d minus 1 dimensional surfaces. Again, there is a parameter r, and you want to cut space into pieces so that each piece will be crossed by at most n over r surface. So here is a general recipe. You pick a random sample of about r, slightly more than r, surfaces from your set, call it r. You construct the arrangement of r, and you somehow cut each of its cells into constant complexity subsets. This is very important in a minute. And then you want to say something like this. Look at such a cell. Okay. Go back just to see the picture. Look at one such green cell. The black lines are those in the sample. The others are not in the sample. So look at the left trapezoid. It is not crossed by any black line. That's how I constructed it. It's a piece of the face of the arrangement. Therefore, it should not be crossed by too many originals. If I sample about r lines, then I expect it to be crossed by at most n over r. Now, as stated, this is cheating. That doesn't work by just saying. You have to work harder to make it work. I mean, this is really the case how you ensure that you hit every target bullseye. You first shoot the arrow and then draw the target around. That's more or less what happens here. If you really want to argue that this works, you have to work a bit harder. Again, let me just play the slide on it. So you still choose a random sample of r log r, about. You construct the arrangement, and you cut its cells into subcells, each of constant complexity. That's the biggest mystery, how you do it. More in a minute. But then you can, if you work harder, you can really argue that with high probability, each subcell will be caused by most of the cells if the frequency is sufficiently large. Now, this is related to the theory of range spaces with finite VC dimension. People in learning theory know about it, and hopefully others too. VC means Vapnik and Chervonenkis, who introduced this concept, then studied in the context of geometry quite a bit. And if you use it and argue and blah, blah, you get what you want. You get that each cell of the cutting is caused by only n over r surfaces, and you need to use, for this, you need to use the fact that each cell has constant complexity. Original cells of the arrangements will not do because they may be too complicated. Okay, here is the same figure again. So how do we do it? Ideally, we want the number of pieces to be the same as the complexity of the arrangement without the decomposition, which is roughly r to the d, if we choose r or r log r surfaces. So this is the best possible, and this is the ideal, but we don't know how to do it in general. So in the plane, it's trivial. You do this, you use something called vertical decomposition. It's a linear version of CAD. You again draw a vertical segment through each vertex of the arrangement, but stop when you hit the next curve, instead of drawing the line all the way to infinity. And then it's easy to see that you get R squared such trapezoids, constant complexity, everything works. For hyperplanes, it's easier to do in any dimension, but let me skip it. In 3 dimensions, with some effort, you can get a near cubic bounds even with the double Cauchy factor, which is nice. In 4 dimensions, it's very hard, but it has been done by Vladlen Kolotu, one of my former students, who indeed proved an R to the 4, nearly R to the 4 bound, but it is open for any higher dimension. If you can just bootstrap using the 4th dimension to bootstrap a bound, and you get R to the 2D minus 4, you add 2 to the exponent for each other dimension, which is not good. But that's the best we know after 20, 30, whatever years you want to do. Okay, now comes the next one. So we had these cuttings. In 2, 3, and 4 dimensions, we can use them to our satisfaction. In higher dimension, we got bounds, but they did not look like the right bound. But we worked and worked, and then a miracle happened. This is plagiarized from a T-shirt of the American Mathematical Society that was around a long time ago. Maybe some people still have copies of T-shirt. There was really physically an earthquake. I don't know how to find the right word to start it. And it was done by 2 notable mathematicians, Larry Good and Nets Katz. If you notice, its first 2 names are interesting. I mean, his parents definitely thought about the connection. So the story behind it, there's a few slides, and let me quickly go through it. It is related to the distinct distances problem of Hertz. I don't think I need to say who Hertz was. In 1946, he wrote a 2 or 3 page paper where he introduced 2 problems, 2 simple-looking problems that kept people awake for ages. And one of them was the distinct distance problem, which he liked. As you can see, quoting from him, my most striking contribution to geometry is no doubt my problem with the number of distinct distances. So this problem is the following. You have n points in the plane, and you look at all the interpoint distances, and you ask, how many distinct distances will you have, no matter how I draw the points? Of course, if I draw the points in general position, you will get n squared and choose 2 distinct distances. But if I put the points on a lattice or some other regular structure, how many distinct distances are you guaranteed to get? What is the mean, the smallest such number, no matter which set I choose? Now, Erdős himself in this paper noticed that if you use the lattice and some number theoretic considerations, the number of distinct distances is n over root log. And he conjectures that this is the right bound. So no matter how the sets, the points are arranged, you will always have at least n over root log n distinct distances. Now, before this earthquake revolution, whatever you want to call it, people worked on it and obtained bounds that steadily went up. The best that they could achieve was this funny-looking exponent. Katz is the same Katz from the root Katz duo, by the way. But again, that was not what people wanted. And then comes, so of course, Gut and Katz deserve all the credit, but the person in the story I like best is Elekes, Yuri Elekes, a Hungarian, very brilliant and very heavy smoker, which actually caused the first line in the next, in the second paragraph. So he thought about the problem and found a beautiful, if I had time, it would really be nice to hear it, see it, a beautiful reduction or transformation from the problem to the problem of incidences between points and lines in 3 dimensions. And so transformation is beautiful, but he needed some property of those incidences that are but which he couldn't prove. But if he could prove it, he would get the lower bound of n over log n. Notice it is not exactly Erdős n over root log n, but considering all the effort that has gone into the problem before this happened, it is, and it's still not, this small gap between upper and lower bound is still unresolved, but everybody thinks of the problem as completely solved. So he passed away because of heavy smoking, fairly young. And then I decided in his honor I worked on it, obtained some insignificant consequence of it, and published it in SOSET, the Symposium on Computational Geometry of 2010. And then Katz read it, started to think about it, found a way to solve the Lekes conjecture, and got along. As an anecdote, the paper at Sausage was by Lekes and Sharir, because it was a bit ridiculous to publish it posthumously, only his name. So people started to call it the Lekes Sharir framework. I kept objecting in many talks that I gave them, saying that I'm not the person, but everybody ignored me, and it is still called wrongly the Lekes Sharir framework, but it's Lekes. So what he wanted and what Katz proved, it's not quite what I'm saying here. They proved an equivalent thing, but it's easier for me to state it in terms of incidences. So they wanted to show that the number of incidences with m points and n lines in 3 dimensions is m to the 1/2 or to the 3/4 percent. When you work on this topic and you become an expert in fractions, and you can indeed see that this is smaller than semi-radian total bound, but there is a catch. You need to, because you're in 3 dimensions, but you can put all your points and lines in a plane, and all you can get is semi-radian total. So you assume that no plane contains more than root n lines, and that forces you to go into 3 dimensions, and then you get the better bound. There is a lot of algebraic geometry dating from the 19th century that is needed to handle it. But what I'm saying is that everybody was excited because Erdős distinct this is a problem was solved, but for the quote-unquote professionals, the technique was the more important one. What is called polynomial partitioning, which is, as usual, running out of time. So let me just quickly say what I can still say. So it came in several installments. The first one was this paper by Katz. And what they showed is the following: that if you have a set of n points in d dimensions, and I give you some degree capital D, you can construct a polynomial, a d-variable polynomial of degree about d. So I'll show you. So if you draw a 0 set, the blue curve, where the polynomial vanishes, it cuts up space into connected pieces, as shown here. And the statement is that every piece contains at most n over d to the d. Now, the number of pieces using fairly standard but non-trivial bounds in algebraic geometry is roughly degree to the dimension. So on average, you expect every cell to contain n over d to the d points, but their achievement was that this holds for every cell. Worst case. Good extended it where instead of points, you have k-dimensional varieties, like lines, surfaces, or whatever, and you get the same result, except that now each cell of the composition is crossed, intersected by at most n over d to the d minus a, which again is the correct bound on average. Again, follows from deep result or not non-trivial result in algebraic geometry, but the fact that it holds for every cell is strong, very significant. Now, So this is good because it gives us a new space decomposition technique that competes with cutting, and it's better from it in many aspects. First of all, you get a correct bound. If you think of the degree d as the r before, you get the same bound, r to the one that you want, r to the d, not r to the 2d minus 4. And it handles varieties of all dimensions, because cuttings could also handle d minus 1 dimensional surfaces. But life is not perfect, and there are various problems. It's very expensive to compute such a polynomial, and you have no guarantee what happens on the 0 set. Maybe all the points lie in the 0 set, and then you got nothing. But still, with some care, there was a decade where impressive results were, very significant results were obtained one after the other, distinct distances of all kinds, incidents of all kinds, many other problems. Some of the problems I label as not in our lifetime before the breakthrough, that nobody believed that they could be solved. Now they are just following. So, still say something before so let me just show you how you do it for the good cuts Elekesh problem. You have m points and n lines in 3 dimensions. Take a polynomial of degree d, cut space by 0 set with the d cube cells, as I said, and each of them will contain m over d cube points by good and cuts, and crossed by most n over d square lines by good. And then the same trivial bound as before, number of points squared plus number of lines holds here 2 for the same reason. So we get m over d cube squared plus n over d squared per cell. We multiply it by the number of cells, which is the cube. We get this bound. And now we just have to use the right value of d, which in this case happens to be m to the 1 up n. You substitute it and you get it. There are all kinds of.
Where did you use the square root of d?
Square root of
Okay,
a.
yeah.
Yes, exactly. That's the next slide. Because this is just the basic idea, but the answer to your question is that maybe all the lines are lying on the zeros. And then there is nothing you can do. You don't know how many. And then you have to work hard. And then you have to use algebraic geometry quite heavily to take care of this situation. But with some effort and so on, it works and the bound follows. Let me see how much more before you kick me. I can say before you kick me out. So, yeah, I guess I can try to wind it down. So the first part of the development led to many combinatorial bounds, incidences, distinct distances, whatever you want. People still wanted to make it algorithmic, because the original construction of cutting was mainly for a divide and conquer mechanism, which we wanted to have here too. That was difficult, and it took some time, but then it was achieved in 2 breakthrough papers, one by Matushek and Topakova, and one by Agarwal, Aronov, Ezra, and Zal. And I'm very happy to say that the first 3 authors here are former students of mine, one of which is sitting here. So it became algorithm. One had to use constant d because otherwise it would be too expensive. So one would not get a single partition, but a hierarchy of partitions. The handling the 0 set is the main issue in these 2 papers, but everything works. And the main application, main algorithmic application, once this was obtained, was range searching the semi-algebras. Now I have several slides to tell you about them, but if you insist, I can keep on talking for a few more minutes, or I can give up. Let me just say what the problem is. So range searching is that I give you a set of points in d dimensions, and I want to pre-process it into a data structure, so that if I give you a region, a query region, a ball, a half space, a cylinder, you can quickly tell me how many points lie in the region, or whether it contains any point or to report the point. So this is range search. So, and the new development allows us to solve it for semi-algebraic ranges, constant complexity. So you can think of a range any way you like to construct it in a reasonable manner, and you want to do it. So up to recently, the first problem is not interesting, it's hardly geometric. The second case, where the range is a half space bounded by hyperplane, was studied 35 years ago with lots of results, but the semi-algebraic thing was open until with the best solution we could get until very recently, until now, more or less. So for half space range searching, the results were two kinds. Either you want fast query time, then you need about n to the d storage, or you want linear storage, and then the best one can get is n to the 1 plus. Again, there are some lower bounds in suitable models, and you can do trade-off with any value of the storage, whatever. And the semi-algebraic case, which was open, has now been solved because of polynomial partitioning. And again, the idea is very simple. You constructed a partitioning polynomial of the degree d. So you have n points in d dimension. You get d to the d connected components of the complement zero set, each containing at most n over d points. And then you make the observation on this figure that the green is the zero set and the red is your range. Now, the range either fully contains cells of the decomposition. This is good because you ask how many points lie in the range, you take all the points in the cell and add them to the count. But if the range crosses a cell containing only some of its functions, then you have to do something, and you do it recursive. So recurse on such cells. And again, algebraic geometry tells you that the number of cells that the boundary of such a range will cross is only d to the d minus 1 instead of d to the d. Some these two like result in algebraic geometry, and each of them has n over d to the d. So you get such a recurrence for the query time which solves to this bound, which is the same bound that we learned very quickly for half space range search. Again, things are not as simple. There are all kinds of issues that one has to work on, but maybe this is a good time to stop because I only have a few extra slides, and I said most of what I want to do, so thank you.